Okay. Okay. Good afternoon, everyone. We are not going to wait for the last student. We are going to start our today's tutorial on HFSS training. For your final project, you will design the LNA circuits. You have to design an antenna as well, and that's a whole receiver system. And the antenna will be your first stage, and it's a very important component for all of you. You can choose patch antenna. Like we are going to teach patch antennas in this tutorial. You can do your own antenna as well. Like where it's not limited. We will provide all the help for all the fundamentals. Like when you do your final project, if you suffer any problems for patch antenna, for any other simple antenna, we can help you. If you do extra work, that means you're going to design very complex antennas. You want show off your skills. Okay, that's extra work. We most likely will not help you on that part, but we hope on the fundamentals. Okay, and today we're going to design a patch antenna on FR4. Like last class we designed LNA on FR4. This time is a patch antenna. I think on Sunday next week we will have the LPKF training. That is a milling machine. We will fabricate both circuits and show you that's also a mandatory tutorial for you. You will have to. So you got all the knowledge from design to fabrication, and in the lab 3 and 4 you will learn how to do the measurement, and that's all for you. You will get all prepared for your final project. Okay, today we are going to design a patch antenna on FR4, and the frequency will be 1.8 gigahertz. Here, is everyone opening the ANSYS electronics desktop? Okay, you can search, and on your computer it's Windows 10. Here you can search as well on your site, and now ANSYS electronics desktop integrates many components. We are going to use the first one, HFSS. Here you can click here, or you can right-click your project and insert HFSS design, and you will get multiple windows. The left corner is the project manager. You can have one. Here is your project, and you currently have one design here, and we can insert more. We can copy and paste. You can do a lot of things under the same project. And on the right hand side, this is the main screen. The main screen here is for the model viewer. Currently we don't have anything, so it's just a coordinate system with grids. If you want to draw something, you can directly draw here, and for parameters later on will be shown here in the property in the left bottom corner. And also when you start your simulation, you will see some message, and there will be progress. You can see how much it is going on, and on the top there are quite a lot of toolbars, and the most important one for us is this one is draw, and you can draw many geometries there. And you can have multiple operations on your geometry. Like ANSYS, first it's a CAD software. You can draw your geometry in this software, and then we do our simulation. Also, you will have model, simulation, results, a lot of things there. So today we are going to do the patch antenna design, and to do a patch antenna, we know the patch antenna is a very simple geometry, 3 layers. In the backside hided, this is a ground plane. If you see the cross-section view, at the bottom is a full ground plane. In the middle is a substrate. Here we choose FR4, and on top will be your antenna. Antenna is this part. This is a patch antenna, and we have a 50 ohm transmission line feed to the antenna. So the first thing before we go to the simulation, we have to calculate what is the width of the 50 ohm transmission line. This is quite easy. You can search it. You can calculate by yourself. You can do we have a lot of calculators. Just put your parameter inside. You will get a width. And here today the width is 2.82 millimeter. And also next you calculate the width and length of your patch antenna. You can follow very classical formulas like this. This can be found in any microstrip antenna textbook. Very easy, and it's very conventional. And you can find online calculators for patch antenna as well. Today we already calculated. So today for FR4 and 1.8 gigahertz, the length will be around 40 millimeter, and the width will be around 50 millimeter. Later on, we will check all of them. We will put these values in our simulation and see if this is at the right resonance. Okay, now we go back to our software. As I said, the first thing is that we draw our model. Like we first have to define the geometry. So let me draw the first thing here. On the top drawer toolbar, we have this one. It's a box, and we click it. Here will be a black spot following us, and here we just draw it arbitrarily. 1, 2, 3. There are 3 clicks. If you first put on your, I will delete it and do it again. First, you will see a black spot here. Put it, drag to another place, click it again, and then lift it up. Then a box is created. Okay, here currently we just draw a box, but we didn't give its dimension, right? So here we can see that in the model tree we have it. This is box 1, which we just draw it. Here if we double click it, we can give a name. For example, here the first box we want to give it as substrate. So I just put sub here. The name is sub, so later on I know this model is a substrate, and I can choose something else here. Color here now it's green. This is fine, but I want to make it semi-transparent, so I can click the last one, transparency, and set my transparency, and click OK, apply, OK. Now you see our box now is being half transparent. This, if we we can also change things here. If we click the substrate here on the left side property, we can do color, transparency, name, material. We can change its properties here as well. Then we have to check the dimension as well, because just now we just arbitrarily draw it. So to change its dimension, we have to get into this detail create box, this command, and double click it. You will find we have the drawing is that we start at a specific location and we give X, Y, Z size. Remember, this is a box, so we first give where we start to draw it and what is the X size, Y size, and Z size. For our design, I want to make the antenna right in the center. So what I will do here, I will like not make it start from middle. I will make it start from here. So that's half minus x and half minus y, and z will start from 0. So here, start from position. This is the x coordinate, so 0.5, and x, I will say this is probably the length of substrate. So remember, you can type it. This is your own parameter. We did not set it right now, but we type any parameter we want. It will later automatically create it and ask us, okay, what is the value of it? This for y-axis is the same, but here we change to width. So you can name your L and width to any name you want. Like you can type full name substrate, you can type FR4 if you want, and the last coordinate is z. Here we start from the z equals 0, so that's fine. And now we click any place, anywhere blank, and the software will ask us, okay, what is your L sub? Because this is our own parameter. So here I will give 100 millimeter, because we're at low gigahertz, so the substrate should be slightly larger. So this is 10 centimeter or 100 millimeter, and click OK. And the width, we do the same, 100 millimeter, and we click apply and OK. Here we cannot see nothing because previously our drawing is so small. So you can press Ctrl D and you will see it. This is at the coordinate of -50, -50 and 0, and the size is quite small. You can see this ruler here. The scale is like 2 millimeter on my side, because we didn't change the x size and y size here. So let's do further. We wanted the reason we give like half minus to the L and the W, because we want to make it in the middle. So here the rest is very simpler. We get L. If we just type L, here it automatically give us, okay, you have this kind of parameter. Then you double click it, your defined parameter will be given. And here same, click W and double click it, because we already define it. And also here we will do this, define a parameter similar for z-axis. Here it should be th, because th means thickness of my substrate. Here is here will be 1.5 millimeter for the FR4 substrate. In this design, we will make it consistent for the for here, and as well as for the last time when we do the LNA design. And we click apply and OK, and we can click Ctrl D again. Now you see we have a substrate right in the middle, and the dimension here is 100 by 100 by 1.5. It's a very thin sheet of FR4 material, but we are not giving assign a material to this geometry. Remember, we just draw a box and create its dimension. We did not assign any material to it. So what we gonna do next is we tell the software this is FR4. It's not metal. It's not other material. So what we can do here, we right click the object, and here we right click it, we'll see assign material. Click the assign material, and we can see that in the HFSS the library is very huge. This is a material library. There are lots of materials already built in the in the library. If next time you find any material which did not presented here, you can add your own material. You just give a name and listed all the necessary parameters. No matter it's metal, no matter it's dielectric, just get its parameter and put it here. Give a name, and you click OK. Your own material can be added to the library. But because we are using FR4, FR4 is a very common material. So here we search it. Here FR4, epoxy, the first one. It's a system material. And you see, this is already selected. Permittivity 4.4 and loss tangent 0.02. This is correct. And after selected, click OK. Now the software knows that we have a geometry, which is our preferred size, and we have the material, which is FR4. And also, why we are using parameters? So the reason is very simple. By using parameters, you can change it anytime you want, and it's good for you to do like parametric simulation. For example, later on, I've found that my substrate size is not enough, or I want to change the substrate. What I can do is, if I feel the length is not enough, I want to make it 200. You can just type your value here, and you don't need to like redraw the whole model. That's a easy thing for us, and this is very useful for parametric, for optimization as well. Okay, here I will return it to 100 for this model. Okay, remember we are designing a patch antenna. We now already defined the FR4 substrate. The next step we are going to do is draw the patch antenna on top. Remember, patch antenna is a very thin layer of metal. So here I will show you the first way to draw it is to, like the same as our substrate, we draw a box. Here, same thing. We draw a box, and this box should be smaller than our substrate. We don't need to be that precise, just draw, then create. Another box is created here. It's called box 1. And first we can like give a new name. This is a patch. We know this is a patch, and later on this could be metal. So the color here, I will choose this orange color because it's probably close to the copper's color. And I will select transparency. You can select your transparency as you like and click OK. See, this typically we choose different color for different materials, so that's very easy for visualization. Also, we have to change its dimension as well. Here we do the same thing, click the create box from the patch, and we have to change here for the patch size, and here we still want to put the patch in the center, so it's still like minus 0.5, and here L, but here is L patch, minus 0.5 times L patch. And for the width we should create another one, minus 0.5 times W patch. I don't think, just one minus. And the Z, remember our patch should be above the substrate, so our start position here is not 0. 0 is the start position of the substrate. Now here should be the thickness of our FR4, which is sub 6 sub. That means it will start from when the Z. Okay, sorry. When the Z above the thickness of substrate, which is 1.4 millimeter. And okay, the length of the substrate we already calculated. It's 39.3 millimeter, and the width is 50.7. Okay, we'll do it here. 39.3 millimeter for the length, and for the width, it is how much? It is 50.7. 50.7. Click enter.瞅一眼他们有没有问题。那边新生，那个别的组的。Okay. And here for X size, we do almost the same as the substrate. Click L and choose the L patch here. And for the Y size, choose W patch. This size is remember Z direction is our thickness. So here we have to give a new parameter, or okay, thickness but not substrate but metal. Thickness of metal. For our design, the copper thickness typically is 30 micron, so 0.03 millimeter, or you can put 30 and here change to micron. Yeah, it's the same. You can do either way. And now this is our patch should be built. Apply, okay. You'll see it looks very thin, but this is correct. If you zoom in, you will see this is like a very thin box there on top of our green epoxy. Okay, make it in the middle. Okay, now we have built the substrate as well as a patch antenna. And next step, we are going to do a feed line. And this time we will feed along x-axis. We will do a 50 ohm feed line here. The feed line is the same layer with a copper patch. It should be a very thin copper layer. So, but here I'm showing you another way of modeling it, which you can use this one. Like this is a box. Here are a group of 3D geometry, but here there are 2Ds, and these are 1D wires. Previously we always using this one. This is when you create it, it will be a 3D box. Now we are using a rectangular, and it's a 2D geometry, but later the 2D geometry can be expanded to 3D. So this sometimes this is a faster way for drawing circuits, especially you have like very complex traces. You are doing 2D filters or other kind of components. Using like 2D geometry and then thicken it would be faster for when you develop such RF components. Now, but the operation is quite similar. Here I will put something close to the middle and drag it till here, which is around the edge of my substrate, and just click it. You will see here we have a new category in the model tree. Here, previously we only have solid because they are all 3D. Now we have some 2D things sheet. That's a sheet here, and this is called rectangular one, and it has no thickness. It's just a 2D rectangular, and similar, we double click it and to change its geometry. The position start here. We have to know we have a trace. The trace in y-axis is our width, and in x-axis is our length. So the length will start from 0, but the width will start from half still minus half point and here is microstrip line. Microstrip line, I put MSL, WMSL, and later on we'll define it. And remember, this is also above the substrate, so the start point will start from the above the substrate FR4. And we click any place, it will ask us to define it. Remember, we calculate the 50 ohm transmission line. It's 2.82 millimeter. So we give a 2.82 millimeter on the width of the substrate, and it's done. Also, for then we have to give a length. Here it's asking us for X size. X size we saw here. It is the length of our trace. So we want from the geometry 0 to the edge of our substrate. So here we'll give 0.5 times, remember, our length of our substrate. The length will be like this. You can directly put 50 millimeter here as well. But as I said, it's better to using parameters for all the geometry. That's easier for later modification. And the Y size is this direction. It's a width. So here, just put W and choose this one, WMSL, and that's it. There's no Z size. This is a 2D geometry, and click OK. Then it's created. The dark green one is your 50 ohm feeding line, and because this is our metal. We know it's metal, so for easy visualization, I will do the same. Change the color, and I will change the transparency as well. Now it's the same color as our patch, but our patch here is 3D. Our rectangular is 2D. What we'll do is we're gonna to make it transfer from 2D to 3D. So we can select this one, and here there is a toolbar here. The middle one, it's a flat rectangular symbol here. If you click it, we will see thicken sheet. Click this one, and it's asking us how much you want thick. This will be this much thickness of metal. Just type it, TH metal, and we click OK. Now if you zoom in, you will find that our 2D rectangular becoming now a 3D geometry. And for HFSS, the basic components are all very simple geometry. We know that in the real world, the knot geometry is as simple as this one. So to make up geometries, you have HFSS provide tools where you can unite two parts. You can subtract one part from another part. You can compare two parts and do an insert, what is called intersect. And here we have already built two boxes. One is our patch, one is our transmission line. So we can select both of them. Press Ctrl and select both of them. And here we click Unite here. Once we unite, you find it, okay. Previously it's two geometry, now it's becoming one geometry. So this is operation of add, actually. You can add A and B together. And from this patch, you will see it here. It's patch, a rectangular box, united with another thing, with another geometry. And it is now becoming a single geometry. we didn't give a still here. The material category is still vacuum. We have to give it, assign it to copper. You click it, and remember we can do material assignment here as well. Here's vacuum, edit. It can go to the same menu, and we type copper. In the system, definitely has copper, and double click it. Copper is selected here, and we click OK. Then now, so far in our model tree, we should have only two things. The first thing is the substrate, which is FR4. Another thing is our patch. On top of it, which is copper. And for our model, we have another layer of metal as a ground plane, right? I'm going to show you another way of modeling the ground plane, not using the box or rectangular here. There's another way, because we know the ground plane is the whole will be the exact same size as our substrate. We will have no. That means we have no pattern on the bottom side of our FR4 substrate. Means the ground plane is full. At this case, we can do a very simple method to model the ground plane. Here, we change our selection mode. Previously, we select objects. By default, it's object. Here we change to face. We want to select a face only. We can select edges, vertex, anything here. But now we're choosing faces. Now, when you click anything, it will only the face will be selected. For example, if I click here, you will find I'm no longer selecting the whole geometry, but selecting only the top face. Then deselect it, because that's not the face we want. We will rotate. When you want to rotate, you can press Alt and move your cursor. We will flip it to the backside, and we click the backside. You will see that here we are only selecting the back face. We are not selecting the top face, only the backside. And here we want this face to be assigned as metal. But remember, this is only a 2D face, so we cannot assign something like here. Only 3D objects can have materials. For 2D, we have to using some in the inbuilt software technique here. We can assign a boundary. We right-click it, assign boundary, and there's one called finite conductivity. You just click finite conductivity. And by default, the conductivity is 5.8 times 10 power 7. This is the actual copper conductivity. So nothing you need to change. And just click OK. You will see nothing here, right? We assign something, but I cannot see where, because it's not a geometry. It's just a boundary condition. So if you go to the project manager and see here, we have a plus symbol and at boundary, and we have a finite conductivity. Finite conductivity is here. If we click it, it will show us, okay, your bottom plane has been assigned as finite conductivity. This is an ultra thin. It's a 2D sheet. But in the calculation, it will be using as a copper. Now we have built our 3 layers, and that's everything for the geometry. Next, we are going to assign for the simulation, pause and set up the simulation. For a micro strip line, we typically use wave port. Like here, in this software, what we are going to do is we create a model here, and we tell the software, okay, this is a wave port. So what we're gonna do is first we change the view of our coordinate system, because our wave port will be here and it will be perpendicular to x-axis. So here we choose YZ, and we draw a model. Choose this one. Choose a 2D planar geometry, and you can click the corner or click anywhere, and you don't have to like select it too much. Just select an arbitrary place. You will see this is now it's undefined 2D port. No, just a rectangular, not a port. And we have to go to the same way as previous. We are going to make it like make it in the middle, as well as make it covering the whole the real port of our feed line. So the first one is for the x coordinates. This is a half of the substrate, so 0.5 L substrate. And for the y-axis, here I will first type this minus 4 times width of the microstrip line, because for we are going to use wave port. For microstrip line, wave port typically will have is 8 times wider than the width of your strip. So and in order to make it in the middle, we start from -4, and here we start from 0, because that's the bottom of our substrate. And here the y size is our width. As I said, should be 8 times. Generally, it's 8 times our width of the microstrip line. And the z size here, you can choose 8 times as well, and will be 8 times thickness by the thickness of our substrate. Different is here is start from -4, and another is start from 0, and also they are both 8 times. Okay. Now you see it's now aligned to the center of our geometry. And this is our port. This is not a different it's a different thing than copper and the FR4. So we choose another color. Here I choose red color and select transparency as well. Now it's becoming red, means that we know this is a port. And also, as a general rule, you have to, for any wave port, if the wave port is not attached to your boundary of your airbox, that means you have to give a PEC backup at the end. So this is a rule when you're using wave port. So what I don't want to like create from like using other methods. So the very simple way is to copy it. You can copy your geometry, edit, copy, or just Ctrl+C. It's the same. And you can Ctrl+V. Here we have 2, but because they are same, so it's overlapped. The only difference thing is we click the new one, and we do the same thing, thicken it, or you can select it. Oh, remember, it's better to suggestion is that we remember previously we are selecting faces. Now we change back to select object, because may give you trouble if you do not change it back. Now we are selecting the last one, the rectangular 3. You can do here as well, edit surface thickness sheet. It's the same thing. It's the same as you using here. And its thickness is here. It is just a PEC backup. So the thickness is not important. I'm not going to use parameter here. I know definitely 100% later on I will not sweep this one. I will no longer change this one. So I just take 1 millimeter, and you will see it. Make sure when you do it, it is the thickness grows to upward in your model. It's not grows in the reverse direction. If it goes into the reverse direction, here you just change it. In case I'm not, it's just to show you what if you find it is on the not on the right side, you just give a minus sign here. But since I'm right, I'll change back to 1. Apply. So it is growing towards the outside. Okay. And here the material is not vacuum. Assign material. Same thing for the same operation as previous. And here we type PEC. PEC is perfect electric conductor. And select it. You see the conductivity is almost infinity. It's very, very large. And click OK. Now it's assigned as PEC. Okay. Before we go to simulation, I want to clarify one thing. Let's look at the slides. For patch antenna, if we feed like this, there will be a problem. The impedance if at this location, if you feed here, the impedance is very high, and it's very hard to match with your 50 ohm transmission line. I'm not going to simulate the whole process, but there are some results already provided here. For example, this is one microstrip antenna, and it is fitted along the port. And where's the result? Okay, then it goes through, and here this is the result. This is because you did not optimize the impedance matching. You have a very high impedance load, but your transmission line is 50 ohm. You will see a mismatch there. And in the previous, what we typically did, there are 2 ways of solving this problem. First way is we cut two minor slits there, like this. That means we are feeding not at the edge, we are feeding to the inner side. So the impedance, we can select the R here until we find a position where the load impedance is 50 ohm. Then it matches with our transmission line. Another way is that we do not do that. We add another quarter wave impedance transformer. No matter what the impedance is, we design a quarter impedance transformer with Z1, and the Z0 here will be 50 ohm. We can do either way. Today I'm going to do this way. So, and I will show you like how can we like choose the R to get a best matching. So to our geometry, we know this is not an optimized one. We have to cut 2 slits here from this place. Here we should need to cut a slit, and symmetrically here as well. So Here we change it back to XY, the view of the orientation, back to XY, and here we draw a box. We previously added the patch with the transmission line. Here we are drawing something. Later on we will be subtract these things from our design. Here we locate it to this position and we draw something with a certain thickness. It can be up or down, no matter what. We will edit it later. A new box is drawn here, and we create a box. Double click the create box. We're going to edit it. And we can check it. The X position we want it started at this position. Okay, this is slightly complicated. The X. Okay. Time for a break. Okay. Here the x-axis, x coordinate system will be in this direction, so it should be half of the length of the patch antenna. Sorry, patch. This one, and the y direction, we will start from, this is 0, so it will start from minus half of the transmission line width. So should be 0.5 times width microstrip line. Should be this one. And Z will start from above the substrate, so it's a thickness of substrate here. When you apply, I think this should not move, because we actually start from this position. X-size here will be a slit size. Here, remember, we have to add a minus sign before it, because the X direction, the positive X is here in this direction, and negative, we are going towards cut something in the negative direction, so it will give a negative sign here. But I will give a new parameter, and here we call this L slit. And L slit, I will give 8 mm as our initial trial. We don't need to give a very precise value, just 8 here. You can give 9, 10 as you like. And for the Y direction is the width of it, and similarly we have to go to the minus. So create a new one, W slit here. I name it for the Y direction, let's say 1.5 millimeter, and click OK. Z size here, it doesn't matter, but here for better, since it's better to parameterize everything, I choose thickness of metal, because we are going to cut metal, so the thickness here is metal as well. And we click OK. You will see now we have a green box. The green box is overlapped with our patch. If you zoom in, you will see this green. This is our patch, and this is our green box here. So we are going to cut this box from the patch. But before that, let's do, because we have to do symmetrically for this side as well. So what we can do, we Control C, we copy it. We copy another one, and in the new one, it is symmetric along x-axis, and the only thing we change is anything about y-axis. We should give a minus sign. So x, y, z only change the y component. Y component here is a minus, so we delete it. And here the y side there's a minus, we delete it. So it's symmetric to y direction. We click apply. You see it is automatically created there. And we click OK. Let's check it. Yes. When you zoom in, you will see this is another green box overlapped with our patch. Okay. Now we are going to subtract these two boxes from our main design. So we select our patch, then we press Ctrl, select these two boxes. Here on the top panel, there is a symbol called subtract. We click the subtract. It asks there is a guide like subtract which part from where. So by default, it is subtract box 1, 2 from the patch. This is okay. And if next time you want to change it, you can select anything, change from left, or select anything, change to right. But here we are, the left should be patch and the right should be box 1 and 2. And we click OK. Now our geometry should be created. Okay, so far anything related to geometry, related to the geometry has been established. We have to set up the simulation environment. For any radiation simulation, we have to create an airbox. Like the simulation will not only solve the solution for the substrate and the metal, it will solve the matrix for the nearby environment as well, because we are doing something radiated. We have to give a space. So we choose this one, create a region. It's a red box there, create a region, click it. And here you can choose your padding type. We are changing the padding type to absolute offset. In the absolute offset, you can tell the software, okay, how much millimeter I want to pad. This is typically from quarter wavelength to half wavelength. For our design, 1.8 gigahertz. What is the wavelength? The wavelength should be less than 200. So 200 millimeter, and quarter is 50. So we put 50 here, 50 millimeter, and we click OK. You see automatically there's a box created. It's transparent and the region is vacuum. This is okay, no material. And then we have to tell our software we are going to do a far field simulation. Any antenna is working on far field, so the waves impinging on this box should be absorbed. So we select the box, right click, and assign boundary. In the assign boundary, you find one radiation. In the radiation boundary, nothing need to be set up. Just give a name. The name, just use the default name. Click OK. On the top,
there's a red box.
This red box, create region. And choose the absolute offset. 能关吗？关不了。
Wait like 30 seconds.
Okay, this is force us to have a break.
There is like the percentage absolute offset, and you can like quarter wave. But what is the length of the quarter wave in automation? 50. And above, we just need Yeah, I think it's boundary. Yeah, maybe it's the same.
I mean, it's the same word concept.
The box.
I guess it's just
Yeah. It's my boundary. It's my boundary radiation.
Okay. To check your boundaries are successfully assigned, you can go to the project manager and click the boundaries. In the sub-menu, you will find two. First one is finite connectivity, which is our ground plane actually, and then radiation box. Okay. So far, we didn't tell the software where is our excitation. We make our port here, but the port here is just a geometry. We are not telling the software, okay, this is our excitation. So here, in our this one sheet, as unassign rectangular 2, we right click it, assign excitation, and port. Choose wave port. Typically, only wave port and lumped port is used for antenna simulation. Here we choose wave port. And I think I don't need to change anything here. Just click next, finish, and that's it. When you finish this, the previously is unassigned, but now it's settling. Okay, rectangular 2 is belong to wave port. Also, in the project manager, in the excitation, you will see here, we have give excitations to this port, and this is a, and here's a 1. See, right? This is port 1. Now we are going to tell the software, okay, what is our simulation range? So click this one, analysis, right click it, add solution setup. Here choose advanced. Click it. In the solution setup, choose single frequency, because this time we are going to simulate a single frequency patch antenna. If your design is multi-frequency or broadband, you can choose them as well. Here, our center frequency is 1.8 gigahertz. So here type 1.8. Maximum number of passes, typically we give 20. And maximum delta S by default is okay. And just click OK for it. Another window should be automatically pop up. And here it asks to check the sweep type. Sweep type, remember, as long as your geometry is not that complex, discrete should be always used. Here choose discrete. And here we are going to set our frequency sweep. Here I will start from 1 gigahertz to our center is 1.8, so I will end at 2.6 gigahertz. How many points? I'll put 33 points here. And we can save fields here as well. Save the fields. Okay. And that's it. So in the project manager, one thing left is that we, if you want the software to calculate your far field, you have to set radiation here as well. So click the last one, radiation, right click it, insert a far field setup, infinite sphere. Here the phi is from -pi to pi, and theta is from 0 to pi. However, since we are in the X, we are putting our patch antenna at the XY plane, and for our chamber, remember in your lab 4 you are going to measure antenna in the chamber. In our group's chamber, the define is different from the software. So to make it consistent and to minimize your trouble in your final project, it's better you give 0 here. Phi is from 0 to 180 to pi, and here theta is from minus 180 to 180. So it's just sweep these two and click OK. Now I think we are good. We designed the antenna, and we have set all the necessary simulation setups. So the next we can click this design and right click it and validation check. Let's do a validation check. You should have everything passed if you follow me correctly. Okay. Then you can analyze this. Right click it again and click Analyze All. Oh, you can save it. I was 随便吗？好，可以。Save the project to any place you want. The simulation should be started.
Why did we choose waveport in this case instead of the lumped one?
For waveport is better because waveport can later on I will show you one thing. You can check the port impedance. Like the working principle of waveport is that it will extend it to the infinity, that using the same cutoff plane. So, for example, next time you design a, let's say, 70 ohm transmission line, it will automatically create infinity long 70 ohm transmission behind it, but you cannot see it. That's a principle. So if you put a lumped port, you can only treat this as a 50 ohm port, or you have to assign the port impedance by your own. But using waveport, you can later on check, okay, is my port 50 ohm? How far is from 50 ohm? Okay, this is a better thing.都跑上了吧，是吧？不知道他们这个跑多久。
What's the difference between model network and terminal one? That's something like.
You are terminal or model?
No, I mean model, but it used to be terminal. So I want to know if what's the difference between them?
I thought the difference should within HFSS. It's not much difference. Mm-hmm. I don't remember which one don't have lumped port. Which one? Terminal.
I think terminal doesn't
have lump port, so that's only thing different, I guess.
Okay.
Yeah, typically we use model network.
Yeah, exactly.
Yeah. From my side, it's finished. Over your side?
Almost.
哎呀，刚刚好，还有15分钟下课了。 All finished? Okay. Now we continue to check the results. So in the project manager tree, here this is the result, but it contains nothing because we have to check them one by one. Here, create, right-click, create model solution data report, rectangular. This is to see the S11. Here, by default, is selecting S parameter S11 dB, and sweep x-axis is frequency, y-axis dB S11. That's what we want. So by default, it's correct. So click new report, and we will see that you should see a very similar S11 plot compared to my simulation. It is matched at 1.8 megahertz and the 10 dB bandwidth here. How much? Let's add a marker. Right-click the blank one, you can add a marker. Here, we will add a Y marker. If we add a Y marker, you will see something here, and you can drag it to any place. Since our 10 dB is our standard, so I put 10 dB here, roughly. You know, this is our bandwidth from 1.77 gigahertz to 1.82 gigahertz, 50 megahertz bandwidth. Okay, then we have to check the far field as well. So for the far field, we have to choose a different one. Far field report. And here we choose 3D polar plot, because we first check the 3D one. And by default, here in the context solution type, we change to sweep. And the category here, GAN total, the units should be changed to dB. And we check the here families, 1.8, which is our center, so it's okay. We click new report. You'll see we will get like 2 dB gain for this design. If you want to check 2D far field, this is the same as well. Create far field report and do this one, radiation pattern. In the radiation pattern, same, we change to dB. Similar, we change to sweep, this one. And in the families, remember we have to select our own file. Typically, we choose two plane, E plane and H plane. In this design, it's 0 and 90 degree control. So you select 0 and 90, both of them. So it's in this way, 0 and 80, sorry. And click new report. You will see a radiation pattern, 2D card. And here you see two traces. One is 0 degree, one is 90 degree, E plane and H plane. They are identical. Also, we can check the antenna radiation efficiency as well. That's a very important parameter. Create new report, antenna parameters report, rectangular. And here we have to choose sweep as well. And for antenna parameters, choose this one, radiation efficiency. And the function could be none, could be ABS, anyway. So we just check our x-axis frequency, y-axis is radiation efficiency, and click new report. It should calculate for a few seconds. Okay. After finish, you will see at 1.8 gigahertz, radiation efficiency reaches to the peak, but the peak is not much. Right-click it, you can add a marker. This is a normal marker. So it's only 32% for the radiation efficiency. That means that's a huge loss. This is FR4. Also, we can check one more thing. That is the port impedance. Like we choose our width by ourselves. We want to check if this is a really 50 ohm. Okay, what we can do here, we create a model report similar as our S11, but here we choose this one, port Z0. We only have one port, so it's okay. And real and imaginary should be 0, but I will select it as well and create new report. You will see our port impedance, it's not perfectly 50 ohm, it's 51, and the imaginary is almost 0. This is the port impedance versus frequency. Because this is a TEM mode, quasi-TEM mode transmission line. If you check waveguide, you will see a curve like this, from hundreds of ohms drops down to 300, and you will see a clearly cut off frequency for waveguide. But this transmission doesn't have that. Okay. I think that's everything we need to check for basically for antenna. Last thing, we are going to, if we want to optimize this antenna, what we are going to do is we click this one, Optimetrics. We add a parametric sweep. Here, the most sensitive parameter is the slit length. So the variable here, we choose L slit. Our initial value is 8 millimeter, and we here, let's say we start from 6 to 12, and with a step size of 2. We add, and after that we add it's to the right box, and we click OK. In the option, we save fields and mesh. This is good for you to debug sometimes. And we click OK. Now you will see we have a parametric setup in the Optimetrics. Now right click it and click Analyze. It will start a group of simulation. And later on, we can update our plots, and it will show you like which lens will give us the best impedance matching. 还有啥东西？没了。
Maybe it's for support. Yeah, for support. Then and go to colors, in file, and select this. 10, you have to select 0 and -6. Oh, okay, so it's color.
The data is actually the same. Just the
Sorry. Sorry for that.
Yeah, the directing. Copy. Yeah. If you want the color one, it should be radiation pattern.
Okay.
Yeah.
That's it. So now I do the same thing.
Same thing. Yeah.
I'm learning a lot. Like it's a simple microscope, but I didn't know like the radiation box button there. I drew the box previously.
The automatic box.
Yeah. No, these plots, these are really useful.
Okay.
Yeah, is there any difference between the results if you use this box versus just a normal box?
No. Data will be the same. The style is different.
I see.
I thought you guys are very familiar with
No, like we are. I mean, yes, like we designed a lot of things for Professor Atik's course, but still, you have like some tricks.
Tricks?
Tips and tricks.
Okay. I'm lazy. I have to learn tricks to save my time. How much is it?
It's so amazing to.
Oh, amazing.
Mm.
什么情况？我看一下啊，不知道，我看看我的。不要啊，这还翻车了。I'll check my results. I saw lots of you. The simulation is not that fast, so what basically you can do is go back to the first one, because we're going to check the impedance matching with our new parametric sweep. Double click it. It's here. Nothing needs to change, but in the families, the slit length, you can choose all of them. That's what I have. What I have when we click apply. Okay. When the slit length is too long, the impedance shift shift to a shift a lot. I have no idea why this frequency is shifting that long. Okay, but anyway, previously our RL is 8 millimeter, and you see that if we switch to 10, the impedance bandwidth will be much wider. Compare these two. So for this design, 10 should be a better one. So, but there may be 9 or 11, around 10 would be better than it. So next simulation, what you can do is to change it. Previously, we switched from 6 to 12 because I already got a result that 10 should be the best optimized value. So here I will switch from 9 to 11 with a step size 1. And ideally, this should be the last simulation for me, and it's okay. I will analyze it again. For you, since you didn't finish, so this will be your last one in the class.
It's not even how to do it. It's not even like a call. To be complete.
少也不是这样的。在那个就是这个 setup 路径。可以选 Pro， 还算是合理的。